Let's see. I'll go through the homework. Let's see. I, uh, so let's see. All right, so let's see. So the Clausius-Clapeyron equation, right? The Clausius-Clapeyron. So people did that pretty well. And then the assumptions. So the assumptions for it are, the first one I think no one got is that you have an equilibrium. Like you have to, when you first derive it, you have like PDV and SDT, and you say it's equilibrium. So the two things. I don't think anyone said that. And then the second assumption is that the volume change can be expressed just by the vapor volume. So you don't need the liquid volume. And then the third assumption is you can use the ideal gas law. Right. So those aren't appropriate for this because the pressure is high, it's at low temperature, so it's not ideal. So he gets around that by sticking this compressibility factor in. Let's see. So he sticks, instead of having just delta H over R, he puts in the compressibility factor, and then that compressibility factor he calculates using the, I guess he's using this little red like Kwong equation, which is something like the Peng-Robertson equation. I think the other paper, like the original paper, or let's see, this equation for use paper uses the Peng-Robertson, I think. And this one derives that equation. Anyway, so I think one group didn't get the assumptions on that. Then B uses this compressibility factor. Let's see, B, they want you just to derive that with the compressibility factor in it. So I think everybody did that. And then because you do that, then that's for a real gas. So that accounts for the pressure, that accounts for the things that were talked about in the first part, like the temperature and pressure. It's not an ideal gas anymore. So that can account for that. But what it can't account for are like the complexities of it. Like, that this clathrate has like holds on to the molecule and things like the other processes that go on. So that's why he has to go from that equation to this equation, which has the kind of the Henry's law constant. It's got a bunch of things about how basically that process goes on. Like add that into the equation. So is it ease of Peng-Robertson? So this part people didn't get at all. Like, what is a cubic equation of state? So should go through that. Right. So cubic equation is an equation that's got a cube in it. Right? So we have like x cubed, we have like ax cubed plus b x squared plus cx plus b equals 0 is a cubic cubic equation, just got a power 3, right? So then, I mean, people said like PBT, so you have 3 things, that's why it's cubic, but that's not it. Okay, so the question is, that's a cubic equation, what's a cubic equation of state? So the van der Waals is a cubic equation of state. So you have P equals RT over V minus B, right? So that would be a linear equation of state if you didn't have the next term, because so a linear equation of state would just be like Cx plus B. But so you have like P equals RT over V. So you just have one kind of density here, rho RT to the power 1. That's linear, right? So then if you add in the minus A over V squared term, so it's a binary interactions and it's an attraction, so that reduces the pressure. Right, so then that becomes a cubic equation of state, even though the power here is 2. Say, how's that cubic? So you multiply everything by V minus B, so you have V minus B times P is RT minus A over V minus A over, or plus A over V squared, right? And then you multiply everything by V squared, and you have V cubed times P minus B squared equals V squared RT minus AV plus A over B. Yeah, that's right. So then you have the cubic term, and then these two terms like group up. So you have this form x cubed. So A is P, B is minus BP minus RT, and then C is A, and D is A by B. Right, so it's a cubic equation. The cubic equation. So if you find the roots of that, so if you plot that equation, it's gonna have 3 roots, like that there. It's gonna have 1 root, 2nd root, that root. It's gonna have 3 solutions to it within a certain range. Right. So it's got, it's one, and this is plotting against whatever the parameter is, which is a density. Plotting against the density, it's gonna have 3 places where it can solve to 0. Right. So the low density one's going to be the vapor, the high density one is going to be the liquid, and this one is like the Neverland one. That one doesn't exist. Right? That's not a real one. So in that region we have 2 phases present. So you have like P versus rho, and then this is vapor, this is liquid for 1 over volume here. You have the critical point. So in this region, you have these 2 phases that are in equilibrium. Those are the 2 roots of the cubic equation in that region. Now, if you go into the vapor phase, you just have 1 root. So it's got something like that. When you go into the liquid region, it's only got 1 root, something like that. Right. So the root is the solution to it. At low density, at certain temperatures. So this is going to be different temperatures. Like this is the vapor phase, that's high temperature, this is low temperature, and this is temperature 2 phase region. Right, so it's kind of how the cubic thing is going to work. I mean, you can plot that out in Excel or something if you want to see how it behaves. Or you can use that. Well, the thing Robeson thing doesn't, the Excel sheet doesn't exactly plot it out for you, but it gives you the 3 roots. I mean, if you mess around with that Excel sheet, it'll give you the 3 roots of this. And then, so that's it. Like this equation, let's see, the van der Waals equation. So you have excluded volume, this attractive potential, and then because this is squared, that gives you a cubic equation. That ends up giving you this cubic equation of state. Right. So people talk about cubic equation of state, and that's what it means. Right. So nobody figured that out. It's kind of weird because that should be like the first thing you do in thermo at undergrad, like cubic equation state. It's like the basic thing, So any questions on that thing? It's not PVT, even though that is three things. So you think like cubic is three, but all right. And then so to account for, so it allows you to have a liquid state. That's the major thing that it accounts for. I mean, you can't have a liquid with an ideal gas because the atoms don't interact with each other, so you can't form them. And then since this claythrate hydrate is a crystal, you can't form a crystal either with ideal gas, right? So it's a crystal form, and then it releases the methane to the solution, and the methane escapes into the atmosphere. And so there's like two things happening. That's why in this equation, he's got like two things. One is like the one is this Henry's law for escape from the liquid, and the other one's this enthalpy of escaping from the claythrate from the crystal. So release the methane from the crystal, and then you have this release from the water to the air. Right, so there's like two stages to this thing. All right, so that business. Then this cubic equation of state is something you're gonna have to. That's like everyone talks about the cubic equation of state. Like they'll say Dabalistic cubic equation, like the Slovak and whatever he uses in this paper. He solves it with the Slow-Redlich-Kwong equation. I think there's a Kwong equation, there's a Redlich-Kwong, there's a Slow, there's like three different equations of state. Each one, they're just modifying for petrochemicals, mostly, right? So anyway, so they're all cubic equations of state though, so they can all be written in that form, like x cubed, x squared, x, and then some other number. And then once you get them into that form, you can equate those parameters with features of the system, right? So like in this case, let's see if I did that right. So I said, so the cubic term, what did I say the cubic term was? P cubed times P. So this term, the cubic term is just pressure, right? And then the second order term is going to be the excluded volume minus RT times pressure. Then the RT equals PV. So this is PV. So it's going to be like the volume and the excluded volume times pressure, the B term. Right. So you can see they kind of have some kind of meaning. And then the C term is just this attractive interaction term. And the D term is a ratio of attractive interaction to excluded volume. Right, so this, when you put it into this form, the numbers, the prefactors have some kind of meaning, and so no matter what equation of state used, then the enthalpy is going to be in the cube term, kind of the volume thing, or the kind of the volume things are going to be in the B term, and then the C term is going to be this interaction, and D is going to be the ratio of those two. Right, so no matter what equation of state you write, they're going to have the same kind of format. So you can say, what is the interaction in this Slow-Redlich equation? That's going to be like the term that modifies the x cubed. So you can use this kind of cubic expansion to kind of say what the things are from a really complicated equation. In other words, you keep adding terms, then that equation of state will become much more complicated than the van der Waals, right? So anyway, so that's kind of how that works. Like, so it allows you to kind of look at it from a different perspective when you write it in a cubic form too. Plus, the cubic always has three roots. So that kind of tells you where things are going. All right, so then D. All right, so D is like, so there's a way to derive Henry's law, right? It's basically the Van Hoff equation. So you derive the Van Hoff equation, you get Henry's law. That's one way to do it. But there's also this, it says to do it though, that it looks like the Clausius-Clapeyron equation. So can you derive it that way? Like instead of deriving it through the chemical potentials, derive it using the Clausius-Clapeyron equation. right, which we did. So go back to that single component. Somewhere we did process clap on, derived it here. So you said like there's equilibrium, so the chemical potentials are equal. So in fact, that's the answer to like question A or something, or B. Right. So you get this delta S by delta V, and you substitute for the delta H. And then you get this thing, which is the same thing as ln P over 1 over T. Then our thing is going to be this Van Hoff equation, whatever that is, this thing. So we have, instead of ln P, we have ln K. And instead of delta H of vaporization, we have the delta H of reaction, chemical reaction. And then for the Henry's law, you say that this K equilibrium is a Henry's law constant. It's like an equilibrium constant. So this K equilibrium is like the reactant. So you have a chemical reaction where you have like XA plus XB goes to like XAB or something, right? So then you take this equilibrium constant. So when that thing is at equilibrium, so when the chemical potentials of A plus chemical potential of B equals chemical potential of AB in the reaction, then you have this equilibrium constant. This is the XAB over XA, XB. So it's just the ratio of those things. Right. So ln of that K equilibrium times R is a change in the free energy for the chemical reaction. So if you have something like it's YA, XA and YA, so the vapor and the liquid, and it's Henry's law and it's escaping out, then you just swap out that the product is going to be this YA. So you say Henry for A is going to be like Y, the vapor phase over the solution phase. Like how that, in other words, XA, the mole fraction in the solution times the Henry's law constant is going to equal the vapor pressure, the amount in the vapor. And the vapor pressure PA is the same as Y. It's a mole fraction. So YA times P0, which you take as one atmosphere, right? And then that's just PA, same thing. The mole fraction of the vapor, same as the partial pressure. The thing, if it follows Raoult's law, right? So you just do a swap here of you just say that the PA is YA, Raoult's law, and then ideal mixings, the XA goes here, and you just have to swap the things to say that this. So you end up with the same kind of form. So basically, yeah.
The article which is related to there is a vivacity factor at the right at the YA.
Yeah. Yeah, so you could say, so if it's an ideal gas, you say it's a pressure. If it's not ideal mixing, then you say it's a fugacity. Yeah, the fugacity replaces the pressure. Yeah, for a real gas in a mixture, because the pressure is different for a mixture. You just say fugacity. So P over P naught.
Yeah.
Right. So yeah, fugacity isn't really that complicated of a thing. It's just a pressure. It's like what the pressure would be if the thing was an ideal gas. So it is kind of complicated, but anyway, so we have that same form for the Van Hoff, except it's instead of pressure, it's this equilibrium constant. So basically you're saying, and then instead of the vapor pressure, we have this reaction enthalpy, which we're swapping out with the enthalpy of a liquid escaping into the vapor phase for Henry's law. And then this becomes Henry's law constant. And then this is basically like the ratio of the concentrations, right? But the concentration could be the pressure. In other words, if you say Raoult's law for the vapor phase, then the pressure and the concentration are the same. And in fact, oh, sorry. All right, so camera up one thing, PC project, sorry. Anyway, so yeah, I think all you have to do is say Raoult's law, say like the pressure. So this equilibrium constant is going to be like YA over XA. And then this is P sat, but P sat over P naught, which would be 1 atmosphere, gives you just YA. So basically, all you have to do is say that you're using Raoult's law for the gas, and then this derivation becomes a derivation of that. They become the same thing. That's what I wanted you to do, is just say, it's just a matter of swapping out the terms and use Raoult's law for the gas pressure. And then that would give you this same equation from the Clausius-Clapeyron approach. It's just swapping out the terms. So the logic, so the thing is that all these, I guess the point of this question is that there's like multiple ways you can look at every equation in thermodynamics, right? You can look at this Van Hoff equation from the perspective that the definition of this equilibrium constant is the free energy change. Log of that's going to be the definition of the free energy change for the reaction. And then from that, you can get this expression and say that the derivative of that just gives you this delta H. It's straightforward, like the derivative of 1 over t is 1 over t squared. Right, it just comes from H minus t delta S. And then just the derivative of that just gives you this, right? So, or you can go through the approach of of starting out delta G is V delta P plus S delta T dt, and then equate the two phases, then go through the Clausius-Clapeyron approach. You can get the same equation. They're totally different approaches, right? But they end up with the same equation. The two different separate approaches, right? So the point is, there's like many ways to kind of get the same equation from totally different directions, right? That kind of makes you believe that the equation is kind of true, I guess, if you can get it from multiple directions. It also tells you that there isn't just one pathway to kind of get some kind of truths, some thermodynamic truths. There's several paths, there's at least two pathways here, right? So, I mean, another pathway would be just to say, I have like, it's an Arrhenius or an Irene rate, or it's an Arrhenius balance, right? And I have an energy that's balancing between a liquid phase and the gas phase, and that's going to follow like an Arrhenius equation. That would be a different approach, right? The one involves a chemical reaction analogy. First one involves like just using the thermodynamic derivatives of the free energy. And this is just using this Arrhenius concept of an exponential probability of something escaping, right? And then it's just a matter of defining what the energy is. So there's like at least three ways to get, I'm pretty sure you could talk about a rate theory for it too. In other words, the gas escapes at a certain rate, comes back in at a certain rate. Somehow that exchange rate, you could probably come up with a rate. So that would be like 4 ways you could drive the same Henry's law equation, right? And they're totally different conceptual approaches to it. They end up with the same equation. So it isn't like one of them is right and the other one isn't right. It's like there's multiple ways to look at the problem, right? And they all kind of end up with the same prediction. So anyway, I think that's a more important concept. And anyway, nobody answered this the way I wanted them to, right? So at least so far. So I mean, I think I graded half the things that were turned in earlier. And then anyway, any questions on that thing? Or I took out some points, but it wasn't anything that would turn off thing. You'll see later on that we'll have several other equations you can derive from like multiple different ways.
Just my opinion, but you should make a question which have the answer in internet article and any document.
Well, I'm trying to get you to look at this I hope you can see that I'm trying to get you to think about it. And just try to figure out like how you would do that. I mean, if you had even attempted to do that, it would be more than full credit. But nobody even attempted to do that. They just kind of spit out what's written somewhere. I mean, isn't it interesting that you can get it from 4 different ways, the same equation? Like, and you can frame, I mean, you can frame the problem in the context, in a different context, in 4 different contexts, and end up with the same answer.
That was interesting because the first suggested the first set of the equation is the Dr. Yu, and he used the equation only with his imagination. So I have to track his genius thinking in life. That was interesting, but the Yun is that can be searched in the Google Scholar.
Right. Yeah.
His published articles can be found in any one site. So
I see.
the tracking was so hard.
For this guy? For which person?
I mean the reference of that article about
Oh yeah. Okay.
24.
Like this?
I mean the paper of
This one. Oh, Yoon.
yeah.
Oh yeah, Yoon, the Korean. Okay. Yeah. He's Korean, right? But he's in Japan somehow. No, weird. Misplaced. Yeah.
Is it possible to email you the answer before we turn it in, so you can kind of let us know prior, so that way if it isn't to your satisfactory, kind of fixing, is that possible?
If I can share it with everyone in the class, your answer.
Go ahead.
And then the answer, my comment to it, I'll share with everybody.
Okay.
That seems to be a fair way to do it.
Okay.
I mean, seems okay.
Okay. And the mail was a little confused because there was a notification that which is the question, which is answer.
Yeah,
it makes me confusing.
Yeah,
very confusing.
I can see that. Yeah.
I put a question mark. It took me, I had to read like 3 times.
Yeah, well, anyway, nobody answered it right so far, so it doesn't matter much, but I mean, everyone just did the derivation of the thing and that was it. So they didn't see like to derive it through the Clausius-Clapeyron, or just from a different perspective. So anyway, it's all right. From this one, I didn't take any points off on that one. It was kind of like, I didn't know how to see, what I found was that this equation doesn't, the equation doesn't seem to work for me. Like this Y number, okay, is 0.0003 or 4 or 3.5. And then 1 over that is 3,000. It's like, how can you modify this first term's ER is an okay number. This number ends up being almost 0. So this becomes 1 almost. And then this is like 3,000 times the value you should have had. So I don't see exactly how that's not a tweak. It's a pretty major, so something's wrong with, something doesn't seem to be right about that equation. That he gets a perfect, this guy gets a perfect match, right? When he does that, like for CO2, he gets it perfect. Like the black is just a little bit, the perfect would be 0 here. The original with Z is the white, the one with just the modification of the top term is the gray, and the black is when he puts that other thing in. The thing, the 3,000. And it only shifts, well, it shifts this thing from 10 to negative something, but I don't know. I mean, I didn't understand exactly where this equation came from. He doesn't explain it. He says something at the top. And then if you actually put in a number for Y, that seems to be reasonable. It doesn't work, right? I mean, to me, it doesn't work. So, and there is no other reference here. So he just came up with this thing.
He's genius or some kind of hacker.
Well, I thought I kind of was waiting for one of you to figure it out. No one No one even maybe you attempted. So you should have, so what you should have done is said like, this doesn't make any sense, like,
Yeah, I just.
you know what I mean? Like you have to,
That what the each term meaning what. This is what I did, just.
I mean, you can email the guy, you know, like this guy is not so famous, right? So yeah, you can email that guy and say like, what the heck is this? Y is 0.0003. This is 3,000.
Any after homework, can you do that?
Yeah, I've done it.
Right.
I've done it routinely. It's like, what is going on here? He might come back and say,
I can say it.
he might come back and say, all right, there's two approaches. He can be a nice person. He'll come back and say, well, there's three approaches. He'll come back and say, no, that equation's not true. That's option one. Option two, and we corrected it maybe in some other paper. Option two would be, he'd come back and explain to you what the actual value of Y is, and it has to be something close to one. But it doesn't make any sense that it would be, because concentration of CO2 in air is nothing, right? So, and then the third thing is he'd come back and insult you and say, you know, so rare that people do that, but there are, the higher up you go in the academic pecking order, the more likely, and especially if option one is actually the true answer, that it doesn't work, then he would be likely, and if he's high up on the academic pecking order, to come back and just insult you. Then you know that this young guy is a loser, you know. So it's at least you still learn something, you know. So it's definitely worth doing that. He's a cited author, so his email is like right here, right somewhere. This is 20 years ago, so he might be dead, but to whom correspondence may be addressed.
Korean university. I can maybe read the
He said, no, he's in, I mean, this is in Japan. Yeah, he might have gone to Korea. Do you know him or? Just, yeah, well, he's at this Japan Energy Institute.
But he
Dance.
can reply easily to the mail with the Korean.
True.
Right?
Yeah, you can type Korean to him. He might be happy to talk to you. Yeah.
After homework.
But he might tell you, don't tell anybody that this equation is bogus. Then it would be a Korean secret. So anyway, who knows? But it's definitely worth doing that. Like it's how you meet people. And it, like, in other words, he can help you, maybe need a postdoc, or you want to get a job at Samsung or something in Japan. Yeah, then you just, you know, this guy, then you see him at a meeting, you go up, oh, I sent you that email, thanks for replying, or you're a jerk, you know, or whatever, you know.
This way can be applied to the homework.
Yeah, no, there's no way to lose in this operation if you start, just contact the guy and say, and definitely I'll give you a sizable amount of points if you do that. Maybe pop the email onto the homework, so, I mean, you know, I've done it before, I mean, people reply. It's, especially if it's something that's being cited and you don't have any idea what's going on with it, you know, like a simplistic look at it, and it can't possibly be true, right? So, I mean, it's easy to pop some equation in and to cite it, and maybe the guy in this paper doesn't even understand, like, that this can't possibly work. So, yeah, so, I mean, it used to be like China, right? So they're in China. So you think like, and all right, they get paid per article that they publish. Yeah, Chinese academicians, and the higher, they go by the citation index of the journal.
Okay.
You get paid by the citation index times like $100 or something, and that's, so you get cash for it.
Yeah, Chinese editors are.
That's why, and that's partly why, if you look at the citation index, you're going to find out like most of the papers, like the journals will say like where all their papers came from. It'll be like US and China are about even, or China's ahead, you know. It's because they're paying per article in China, you know. US you get nothing, so kind of makes sense. And then that also though encourages people to, if the thing isn't working out, and you just kind of force a square peg into the round hole, and like, hey, it worked great, you know. So especially if the guy Yoon is at the this Japanese institute, right? So it's kind of like somewhat high power. So maybe he's not going to go and say that equation's wrong, but he can cite it and just say it worked great. Everybody's happy. So that doesn't mean you have to believe it, you know. So in fact, you should challenge these things when you see it if you can. So anyway, so that's that homework. The D, I guess, turned out to be challenging. D could have been pretty easy if you just said. I mean, to me, it's like Raoult's law, and then you have to substitute P for Y, and then it works. That's it. That's kind of it. You just say Raoult's law, and then kind of then you just say that derivation would work. For the
It's
same.
already given there, PIXI.
What is it?
The condition is already given there, PIXI,
Yeah,
and XI equal to 1 for.
right. Yeah, but so the other derivation's on a totally different subject. Those like chemical reactions. So you have to say something about, because the one is a derivation based on pressure, the other one's based on composition. The chemical reaction one, it's mole fraction. So you have to somehow relate the two. Raoult's law relates the two. If you just do a straight relation, so it's kind of weird you're using Raoult's law to prove Henry's law. Which and they're the opposites of each other, so there's some kind of weird thing going on. But anyway, it's good to do that though, to look at the different approaches to it, because there's insight in it that you wouldn't get otherwise. Right? See, it's a way you can kind of understand from various perspectives. And then there's this. I think it's really important to see that there's this like general rule, this log of something versus 1/t rule, and the slope is the energy. And you see that like over and over again. Yet there's different frameworks where that was derived. There's like 4 different frameworks where it's derived. So, and we'll see it again, like when we do Debye and Einstein heat capacity, it's the same equation that they're using to get the distribution. So the exponential of that ratio will give you the kind of the probability, like the density of states you calculate from that equation. Same thing like an exponential, right? So that equation is good to kind of know about. Anyway, so set things there. I made up a new one. Those are both from last year, those 2 homeworks. This one's from this one's this year. I thought this was kind of interesting. It's this high entropy alloys, which means you have more than 5 components, and it's a substitutional alloy. So you have like brass, where you have a certain crystal structure, and you put in zinc or something to substitute for copper. But this is 5 components, and all of them can swap in. So they call it a high entropy alloy because the things are mixed up. In other words, you get a lot of different states when the things can all have different positions with 5 components. Yeah.
Since I'm reading the article, be a little vexing.
Mm-hmm.
I was wondering, is there anyone particularly we can go to during the time to, like, when you break it down, if we can go to on some parts, if possible?
You mean like you can't understand this paragraph? Who do I talk to?
Yeah, some of the formatting, maybe the language, or if we're getting stuck on like maybe I don't know the Henry's law or something we just aren't familiar with.
Oh, Henry's law you can get from Wikipedia.
Oh, not necessarily Henry,
but,
but I'm saying
yeah.
in general.
This one though has a lot. Okay, so all these papers, they have a lot that you're not going to understand. That you're going to have to get used to. So how you deal with that is up to you. You can try to, like a lot of times you're given something challenging to read. You can, I mean, the natural thing to do is just skip over the stuff you don't understand and get to the parts you do understand, and then just try to go back and maybe piece it together, and then you have a kind of vague understanding of something, right? That's one way, one approach. Another approach would be the opposite extreme, is like, every time I see a word I don't know, I'm going to go find a book on it and understand it, right? That's the other extreme. That takes time, takes some effort, but eventually you know everything if you do that, right? The first way, you're going to be very efficient. The second way, you're going to know everything, and there isn't really a right answer to it. You can skip over things you don't need to know until you need to know it. That's the just-in-time approach. In other words, I'm going to learn it when I need to know it. That's why Google's there, or whatever, somehow, or I'm going to have a network of people I can talk to about stuff. So I think you got to learn how to deal with that, because you're going to get a lot of stuff. Things change all the time, right? So whatever you do, if your master's, PhD dissertation, then you're going to go work at some other thing. You're going to find a job doing something else. And every time you're going to be given this stuff, and you're going to look at it, and it's going to be just exactly the same situation. Here's this paper. He talks about vast. I don't have any idea what vast is. that deals with density functional theory, which I also don't have any idea what it is, you know. So how are you going to deal with that? I mean, you just have to figure that out. Those things aren't important to the homework, but they're the first section of this whole guy's thing. And you'll find out there's people in the class that know a lot about VASP, like they did a master's or something on VASP in South Africa or someplace. And so like if you go to, and there's different groups that would know, like Matt, whatever, the guy that does diffraction, he probably knows about VASP. And you could probably go talk to him and he'd be like jerky, or he'd probably give you some hint about VASP. You know, and you could get a job kind of doing VASP, maybe. I mean, maybe not, you know, but probably not in a manufacturing setting, but unless you're doing microelectronics, right? So it has to do with like quantum mechanics. And then it's like quantum mechanics can only solve really simple things, yet you have these complex things like this whatever, high entropy alloy. So you have to figure out like how the electronic states are changed when you throw different stuff in randomly. And these programs, this density functional thing allows you to do that on a kind of on an atomic level, you know, local scale. So it's kind of a cheat that gives you the answers you need to get about say magnetic moment is one thing we know, entropy and stuff, electronic state, basically electronic and magnetic states of atoms. Anyway, so the first part of this paper, he talks about that and the kind of the games he played with that. And then he gets to the main thing, which is he's trying to make a refrigerator from a piece of metal. So he's got a piece of metal, he's got 5 components, takes a SEM of it, he gets that it's one phase. And then with SEM, you can do elemental analysis, you can do images of the different elements that are in it. He says they're well distributed, so it's one phase in terms of everything, at least on a 10 micron scale. So he's happy that it's a single phase, it's a BCC crystal, it's like the simplest thing he could make. BCC just has this really simple diffraction pattern, just like a couple spikes, you know. That's how FCC would be a little bit more complicated. It's like a pair and a single and a pair. BCC is just like boom, 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 right? So anyway, it's got this, he can say that's BCC and it doesn't change no matter what he puts in. So anyway, so it's got a second order transition. And then and you can use that second order transition to make a refrigerator. Like at the energy change you get with the second order transition, you can use to cool things if you want, just a magnetic transition. So the stuff doesn't change at all, just magnetization changes. It's kind of interesting until you figure out how much it's actually cooling. The amount that it's cooling is almost nothing. Like just, it's not really doing anything. It's kind of a novelty item, right? So anyway, all right, so that said, this area, like this high energy, high entropy alloy area, so these, like the papers in that area have like 2,000 citations, which is a lot in a couple of years. It's like, means like everyone is jumping on the bandwagon, mostly in China. Like this is a topic that was invented in China, and now like this saying is in China, I think, T Lab, whatever. And then and now there's more, so now there's more like this law is in Spain or something, Seville, Spain. So the topic is branching into like Europe and the US, but it's kind of a Chinese topic. So I don't know, it's kind of interesting to look at it. This is another review paper. This is published in Nature, but I only got the I think it says like Nature Review Materials something. So it's a Nature article, but you couldn't get the original one because you didn't pay you have to pay something to make it public, and UC doesn't have whatever. So you can get because these guys are at Oak Ridge, then you can get they have to file the original thing after it was accepted. So that's what's here, the after accepted article thing. So anyway, so that's what this week's going to be about. I'll talk about it tomorrow and Thursday. Any stuff on the homework that? Let's see, so I want to go over here. Single components. All right, so I promised I would go back, and I realized the slide for the Landau, the second order Landau, let's see, where is the equation here? So he's got A and B are both positive. He's got, and their second, like the second, they're all even orders of the order. So order parameter is this thing about the directors are pointing in some direction. And then when it's the gamma 0, when they're all random, and that gamma would have some value and they're all pointing in the same direction for a magnetic material. It's like ferromagnet and paramagnet, a random thing. So the second order transition you get, we got last time with A and B positive. So one way to get, and then so Landau wanted to get a first order transition, which is kind of the most important transition. So one way to get it is to say A is positive and B is negative, and then add a C, which is a 6th order term. So it's a power series, like a Taylor series, but ends up with this C term, right? And the reason for that, so before A would be below the critical temperature for the second order transition. Let's see. So A should be positive, below the critical temperature, A is positive, right? And then above the critical temperature, A is negative. So when A is negative, so this term's increasing faster because the 4, this is increasing slower, but initially at low gamma, the thing drops and then it rises again. So you get a minimum in this free energy. So you have a free energy drop to a minimum and it goes up. It's that magic gamma where you get the minimum free energies is gamma naught. And that gives you this behavior below, because A is negative, below TC. A should be negative below TC. Is this still messed up? T minus TC. This is backwards. It should be T minus TC. I think it's still not the updated version of this thing. Yeah.
Over what Landau theory is trying to say, what it is actually.
He just says, so it started with this thing, right? So you had like a ferromagnet and then paramagnet. So paramagnet, the directors, so there's clusters of atoms that are like 10 micron, 5 micron in size that have a magnetic moment to them, right? So those clusters of atoms can have a situation where all the magnetic moments are pointing in any random direction, or it can be fixed so they all like align up, right? And there's, when they line up, they have a certain like energy interaction between those domains that is good. Like if north is, well, you can think like north and south would be opposite and that would be the best, or it could be like north is good, right? So somehow normally north-south would be the optimum, right? Basically, there can be a reason that they'll align so they're all pointing in the same direction. And then if you go above the Curie temperature, so these things are thermally fluctuating. So temperature makes them spin around and this energy makes them straighten out. So the competition between temperature that makes them flip and then the energy that makes them point in the same direction. So if you're at a high enough temperature, the flipping thing overcomes the same direction thing. And then you get the paramagnetic behavior, like a random. Unless you put a field on it, then it straightens them out. So you can magnetize it and straighten them out. But basically, if you take that magnetic field off, they go random because thermally they're moving around. As you cool it down, you reach a point where thermal energy isn't enough to randomize them, and then they straighten out. So that's called the Curie temperature. It's a second order transition, it goes from that to that, right? So that's what everyone's trying to figure out how that works, right? So Landau said he's just going to have a power series in this order parameter, which has the feature that it goes to 0 when they're random, and it goes to some value when they're pointing in the same direction, right? So you can calculate that by looking at the cosine projection of the arrows. say, take the two vectors that are pointing and then like do a dot product of the two and you get the kind of projection of the two, and you can figure out a number from that. If you average cosine squared of the thing, you can get a number. So order parameter. It's a right. So basically, so the mathematical way to get an order parameter calculated from a bunch of arrows. You mathematically calculate that number that goes to 0 when it's random and goes to some value when it's oriented. Right. So the order parameter has some meaning. You can mathematically calculate it. Say you could calculate the order parameter from this picture. They give you 0 order parameter here and some value here. This would be a value of 1 actually, if you calculate it that way. But then you modify it by some prefactor in energy term. Anyway, so Landau just said, all right, the free energy depends on that order parameter. It's like when it's 0, the free energy is 0. The change in free energy is 0. From the paramagnetic state to the ferromagnetic state, the change in free energy is 0 when it's a paramagnetic state. When it's a ferromagnetic state, it's got a value, right? And that value is going to depend on the order of the system. And it turns out there's a magic order that it reaches at a certain temperature. So if it's a second order transition, it's going to be like a gradual transition, and the order parameter will shift depending on what the temperature is. Right. So how do you predict that? Well, just do a Taylor series in order parameter. And it has to be even because I guess up is the same as down. So it has to be even. It has to be an even number. So it has to be at the only even powers of the order parameter could work here. That was one of his propositions, that only even powers would work. So he just uses even powers. And then he invents this idea that there's a critical temperature where this thing happens, and this temperature difference is the thing that's going to govern it. That temperature difference idea is really like the crux of this operation. This T should be T minus TC, not TC minus T. I think this still isn't the new version of this thing, and I'm not sure why I can't get the new version. It's a problem because this thing is corrected over here and it's not corrected here. Let me just try to download this again. Anyway, so basically there's let me try to find that because this is messed up. Why is it messed up like this? It's the same in the other class. And at home I can get the right thing on this thing. Single prime system. Oh, I know what can do. This is a let me see if this one's right. This is a PDF of the same thing. Yeah, this one's fixed. See, right, this one is different than the other one. They should be the same. All right, question is, how do I get rid of that? Here. Did I get rid of it? No. Nice to be able to look at this. What does that do? Nothing. Maybe download it. Didn't work. Right. Anyway, so this has the right order, T minus TC though. So this thing below TC, this is negative, above TC, that's positive. When it's negative, you can get this. You get this free energy drops and then rises. So you get a minimum, so you can get a magic gamma, magic order parameter below the TC. And above TC, this is positive, that's positive. That means everything's positive. That means the higher the order parameter, the worse the free. And there's a free energy change you want to be negative. You want to have a drop in free energy for the thing to be stable. If there's no drop in free energy, then you just go back to the paramagnetic. So it tries, in other words, it tries to go to orient, but when it goes there, the free energy is higher. So it's not happy. It wants a lower free energy, so it goes back to the random. It keeps trying thermally to organize, but it can't, because every time it does that, the free energy is higher, so it just wants to go to random. It's like spring. So it does order, but it can't stay there. And so when the A is positive, that just always bounces back to 0, so you get 0 order parameter, and it's paramagnetic. Get to TC, and then this thing, and it's a second order transition because this is continuous. The blue line doesn't have a step in it, right? So to get the first order out of this, instead of this this being positive, this is negative, and then you have another term that's positive. So that means you can have like a gap kind of in this thing. So that the so if the free energy change, so say you're in the so if A is positive, right? And then A is larger, A gamma squared is larger than B not gamma 4, then the whole thing is positive. You have a positive change in free energy, then it goes to 0, just like before. But you reach some magic number where this term and that term balance each other out. And that number is this T star, where all of a sudden a different kind of behavior happens, and there's a jump in it. So in this case, this isn't continuous. You don't go blue, 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 then continue on. There's like, and you fall down. Right. So basically that's a first order transition versus a second order. It just continued on. Yeah.
Is Tom over, what is it on the side supposed to be?
This what? Where?
The plot, the graph.
Uh-huh.
So I'm assuming the bottom one is Tom, and what is the,
No. Temperature. Sorry. Small t is time, big T is temperature. Small t is time, big T is temperature, almost always. Yeah, this is temperature. So this is a critical temperature.
over the Y value is what?
That's the order parameter. Like in other words, a number that's 0 when it's paramagnetic and it's some value when it's ferromagnetic.
Okay.
So this is just you want to, what you could say it's ordered, it's not ordered, but there's different kinds of order. It could be like ordered a lot or ordered just a little bit. Or it's biased a little bit towards ordering, right? Or it could be random. So random, it's 0. And then it gets more and more ordered as you cool it down more and more. It's like a second order transition, right? So it becomes more and more ordered, right? So basically that's the second order transition. The heat capacity, which you can calculate, has a step, but the order, which is that's the state function, that's continuous, right? So that in the first order, the state function, there is a magic temperature, but there's this like drop in it, and then it goes back to 0, right? So because of the way this is set up, if you do the same term A, so it's T minus T naught, so this goes negative at low temperature, positive at high temperature. As soon as it's positive and enough to overcome that, then you have the same scenario. Delta F is always positive, means that it won't happen. So it's a change from paramagnetic to ferromagnetic leads to an increase in the free energy. So that won't happen. It only wants to reduce free energy. It doesn't want to increase free energy. Right? So, and then there's this in-between region where, so if you're below this T star, then the A is positive still, but this is more negative than the A. So you still have a negative behavior and then a positive. So you have the same thing as before, you're gonna have a minimum in this thing. Even though it's, so between T star and T naught, A is positive, B is more negative than A is. So that means you still have a negative and a positive balancing, so you have a magic, at that point you have a magic gamma, where you can have a phase separation. And with this setup, that happens at a discrete step in the order parameter. Like there's an on and off switch. It's 0, and then all of a sudden it goes to on. You have ordering. So it's a first order transition. That's supposed to be like a that's supposed to be when you have ferromagnetic to paramagnetic. So when you have like this thing going to that thing. So it's kind of some big, some little, goes to random. Right, that's supposed to be a first order transition. This is supposed to be a second order, going from ferro to para, which is what the paper is this week to look at. It's complicated, but the thing with it is that you'll see these words like the order parameter for a system, and like you just will have no idea what they're talking about. So basically, it's based on this thermodynamic, this kind of Landau model. You have to kind of have some rough idea what it is in order to understand when they apply it. Because when you get to mixtures of like A and B, like red and blue marbles, in that case, the order parameter is the concentration of A and B, like red, blue. And then the same equation is going to be used. So they use the Landau theory to talk about first and second order transitions.
Yeah.
Right. And they talk about the order of the transition. It's all based back on this magnetic thing. So no one understood that stuff he developed the whole field in this magnetism thing. Then it's ported over to all the other fields of transitions. So it's kind of inconvenient, but the magnetism, which is a little niche area of material science, becomes like the dominant, the thing where all the ideas came from. Because at the time it was important. You know, it's still important. You see, like, I guess you can make a refrigerator with it. It's like apparently like from that paper. So anyway, to find T star, the derivatives, the first derivative and the free energy are set to 0. Then you just solve the equations. You can solve for T star. T star ends up being T naught plus this kind of shift factor that has to do with the other terms in the equation. So mathematically, you can get it by setting the derivatives to 0 and then just solving those equations. That's kind of how this works. So the trick is, like, the red thing is the important thing. You set B naught to be a negative number. Like A, B naught, and C naught. I mean, A naught, B naught, and C naught are defined as positive. So to make B negative, you put a negative here, right? And in the second order, B's positive, whatever that is. B's positive here, right? So, and there's no extra 6th order term to deal with that. So you see, like, this is the same, you'll see this same approach. So this stuff, I think this was like, I don't know, when was he alive? It's like 1930 something. And you'll see, like, that this approach of first the idea like T minus TC over T, that's used like over and over again. That'll be like a number like alpha, they'll call it, or tau or some tau, I guess. Sometimes that's called tau, like T minus TC over T becomes like tau, and you'll see things, something plotted against tau. Tau's like T minus TC over T. So, you know, that's like Landau theory using. They're basing it on this kind of Landau theory. So, I mean, even though you don't feel comfortable about this, at least you can recognize like T minus TC over T, and they're calling it tau. That's like a critical number that has to do it when it goes to 0. That's a critical point. So you'll see a plot, and 0 will be in the middle, and everything happens around 0. That's a critical point for the system, right? So that's what I mean. Like, you can piece things together. This is a starting point. Like a Landau thing's a starting point, even though it's confusing, right? It's a starting point to put together like what happened in other things. Like when you look at other systems, and you'll see, if you don't know this, so they'll just assume that you know Landau theory. Then they'll say, like, of course you're going to use tau to do this other thing. So it's like the first step of it. You know, so I think anyway, it's good to kind of glance at it. Your life won't be ruined if you don't understand it totally. All right, then I guess it's just clean up on this chapter. Let me just sit through. Let's see, is there anything else we haven't really done? Went through that. I missed that. Then I mentioned this, but basically this is important. So the compressibility factor, which is 1 for an ideal gas, and then for a non-ideal, you do a power series, expansion and density. Right. So if B is 0, that's an ideal gas. And B is 0, A is 1, that's an ideal gas. Right. And then B has some value, then that's a non-ideal system. Right. And B has something to do with excluded volume. So it's kind of like, if you see, it's rho squared here. Like if you have rho here, if you multiply this by rho, you have A rho. That's a first order. So that's just the thing. That's like a gas atom alone, like an ideal gas. It's isolated, right? So, and then rho squared means binary, like 2 things hitting each other. Or you could, so there's like many ways to look at this. So you could also say A times rho is a spherical object. Okay, and then B can have to do with asymmetry, like if a thing becomes a cylinder. Like say you're looking at mixing tobacco mosaic virus into water, right? And it's rods, like rigid rods, or DNA and water. So they're rods, so they're not spheres. So in that case, you can calculate B for the solution of mosaic virus into water according to the symmetry of the object, like the asymmetry ratio will give you B. You can calculate it from that. So B can, because the rho squared also has to do with symmetry. Now it's put in one other axis, so a rod has one other direction. In that case, C could reflect if you have three-dimensional asymmetry. In other words, it's not a rod, it's like some other thing, like a person, it's got 3D to it. So then you need A, B, and C. So usually the only terms in this people use are like A and B is usually dealt with as a binary interactions. I could say C is ternary interactions. Like if you have one atom and another atom interact, then their interaction together coupled has an effect on another third one coming in, like it would interfere with it somehow. Like in other words, the third atom can't approach the first atom from that direction because the second atom is already there. So that would be C. Or there could be other more complicated things like the whole potential of the system changes when two things bond or kind of interact, right? So anyway, C could reflect some kind of complicated thing. No one ever goes beyond C. Rarely do people go to C. Like if you look at C is used to describe, like if you have a polymer chain and solution, then you use A and B. If you want to look at that polymer chain when it collapses or if a protein folds, like if you have a protein in solution floating around, then its interactions with other proteins would be B. Then C would be the protein collapses or folds into some structure, like a functional structure. And so the C term can be used, usually in desperation, people add the C term. When something is too confusing, they can't figure out what's going on, the third real coefficient shows up to save the day, kind of, right? But as far as really understanding C, it's not exactly that easy to figure out. B is pretty simple to understand. It's just kind of the excluded volume, right? So you can do is take, let's see, I got to do that too. What you can do is take the van der Waals equation. So we have the ideal gas law, PV is RT. You have excluded volume, which increases the pressure. So if we say it can't go here, the pressure has to go up because it has to go somewhere else, right? And then we say, I want to have a liquid state. I want to have the things coalesce that would reduce the pressure. And it's a binary interaction we're looking at. So you have A by V squared, which is rho squared, right? So 1 by V squared is rho squared. So this already looks like a kind of a viral expansion, right? So if you equate this Z with the Z from this guy, you can get this expression, which expresses it tells you what B is in terms of these things that van der Waals, they're pretty concrete what they are, whereas B is a little bit more nebulous. B is just a power series expansion. So, right, so B is the excluded volume, and then it's minus, so A has a value of an energy because PV is energy, right? So A would be energy by V squared, kind of gives you the A's in energy, more or less, right? So A is an energy, so you divide it by RT to normalize that. So A is relative to, so as the temperature goes up, A diminishes. In other words, as things wiggle more and more, this attractive potential becomes less important, right? In other words, you have an attractive potential, and what's fighting it? Everything from collapsing down into just nothing, right? Temperature is making the things move around and shake apart from each other. So the ratio of that energy, the attractive energy versus this kind of temperature energy, the RT, gives you this kind of the volume, that gives you units of volume. If you figure out from this equation, A would end up with units of volume. A by RT would give units of volume because PV is energy. So if you divide A by PV, you'll end up with energy for A. Energy, you end up with volume times energy for A. So anyway, A by RT is volume also. So this is the compressive volume that's leading to the liquid state, right? So B is like taking account of the solid volume that actually the thing excludes, its physical volume. And A, this is kind of like the soft volume that the thing is trying to attract. So it's a negative, it's dropping that volume because it's got an attraction. And the higher the temperature, that thing will disappear if you go to high enough temperature, which means there's a magic point where there is no excluded volume. There's no BT. I could set BT to 0, then I can get the temperature where B is 0. That's like the magic, the critical temperature. That's like the TC from the other thing. Right, this expression says I have ideal behavior, so I have Z is 1, ideal behavior, and they have non-ideal because of the interactions. B contains both interactions. It's got the hardcore and the attractive potential. So if I set B to 0, I'm back to an ideal situation, but with an object that has excluded volume, but the attractive potential overcomes the excluded volume in terms of thermodynamics. Right, so that's the critical temperature. Below that temperature, it's going to collapse out. Above that temperature, it's going to be floating around. Because above that temperature, RT overcomes A. Below that temperature, it doesn't. Right, so there's a magic temperature that comes out of the comparison of the van der Waals with the viral expansion. The critical temperature, TC, which is the same thing as the Landau TC. Right, and in fact, you can write this TC in terms of T minus TC over T from that expression, then you can get tau, which is like this number that's going to decide the behavior of systems in terms of the critical point. Right. So that isn't boring you enough. These critical points become important, like you can reduce everything according to the critical values of the critical for the system, right? So this is showing that 3 roots to the cubic equation, showing the 3 roots of the cubic equation, same thing. And then what did I miss here? This thing, let's see, which is important to the paper. So let me get back to this. I didn't find it. Let me do that. Blah, blah, blah. Not this, sorry. First order transitions. Not this, right after this. Phase diagrams. Degree of freedom, I didn't mention. This thing. All right, so we got, before we got the Maxwell equation, so the horseshoe things like PS at constant V. So negative PS constant V is going to be the same as TV at constant S. Right, so there's 4 of them in this diagram. Right, there's like PS constant V, SV at constant T. It's going to be PT at constant V. Right, all the 4 Maxwell equations. So this all came from this approach that I briefly mentioned, I guess, of the Legendre transformation, which is kind of simple and kind of complicated. Right, so anyway, so if you write, so in this paper, he's doing magnetic field, right? So B is a magnetic field. Let's see, B is there's a magnetization and the magnetic field. So M is magnetization, magnetic moment, and B is a magnetic field that you put on the system, right? And the M times B gives you energy, right? Just like here. So we had the terms that would go into the derivative of the free energy be like BdM or EdP, or the charge, the voltage versus the charge, change in charge, PDV, right? So this is for magnetic system, it's BdM, right? So the question is, like, so he's trying to find, like in this paper, wherever that is, let's see. Let me just go back to that. So he's trying to find, there's a plus here somewhere. He's trying to find this delta S, because that will be a definition of his second order transition. He gets a peak in delta S for the magnetization at a certain critical temperature, TC, right? And when he goes to these high entropy alloys, that TC goes to room temperature, and that makes his refrigerator work better. That means he's refrigerating things that are like kind of human scale versus some other odd thing that would be needed. So he needs to calculate this delta S, but he doesn't have any technique to measure delta S, right? So he needs a Maxwell relationship, because he can measure the magnetization with a magnet, basically, see how much torque you get when you put a magnet next to his thing, or some other machine that does that as a function of temperature. He can measure that dm dt, right? And from dm dt, he wants to get delta S. So to get that, that's, you need this thing, that ds dm, that the field with respect to temperature is going to give you the delta S that he needs from the system. So you can measure the field, that's his input, temperature's his input. You can measure the magnetization, then you can get ds if he has this Maxwell relationship. And ds is the thing he wants to qualify where he's getting cooling from his refrigerator, right? Because ds times T is going to be the energy that he's absorbing in his refrigerator. So anyway, so how do you get that expression? You know, it's a Maxwell expression. So you take the same, so you take the Helmholtz free energy. So you have dA is S minus S dt V dP, right? And then you go back and say, well, what if I have a magnetic field BDM? So I just add in BDM to that. And then you say you're going to do this at isochoric, so dV is 0. Somehow you keep it at constant volume. I mean, it's a Helmholtz free energy, so it's kind of at constant volume anyway. So you drop out that term, you just have SDT and BDM, then you have the things that you want. Those are the terms that you're interested in, right? And then you say A is in this system at constant volume, A is broken down into a temperature dependent and a magnetic field dependent term. And then dA dt at constant M is delta minus S, and dA dm at constant T is B. Right, so you can just write that dA in terms of those two terms, dt dm, and you have these differentials in the front, right? And then you take a second derivative, but you take a derivative with respect to T, so the T cancels out, and then you take the derivative with respect to M, so then you have the M cancels out in 1, and you have dt, so you have dA, you have with dA dt dm, or dA dm dt. There'll be the second derivative of A with respect to M and T. And from that, because you know what dA dm at T is B and dA dt at M is S, then you can substitute back in for those two terms, and then you can get the Maxwell from that. So that kind of taking a derivative expression, then taking the second derivative with respect to another term yields this kind of Maxwell expression, right? Anyway, you have to kind of look at this and see that could possibly work. You never actually have to do this yourself, but if you do this, then your 4 Maxwell expressions that you got from this becomes 26 Maxwell expressions. And if you include the electric field, so there becomes a lot of differential relationships for any system that you're looking at, as long as you have a way to park another term in here, right? So there's a paper on that subject somewhere in the web page. There's a guy from MIT that wrote a whole book-like paper on this subject. It's somewhere under this thing about how to do these different, Alberti, this thing, General Chemical Thermodynamics, use of Legendre transforms to do basically everything. This is a long paper. He goes through every possible kind of Legendre transform to get Maxwell equations, to get the 26 Maxwell equations, from normal, magnetic, electric, TP, whatever systems. And he goes through more than that even in here. So you have to be an aficionado of thermodynamics to take a look at that paper, but if you happen to be. Anyway, our paper uses that, and the homework asks you to do this derivation, do the Legendre transform to get that thing to. So you'll have to go through and figure that out at some point, right? So anyway, I think that's about it for this section. The thing I didn't do is Gibbs phase rule, which I think you might, and I didn't go through what CalFad is, but CalFad we'll need for the next chapter, next section anyway, So I'll mention that. And then I guess that's about it for today. And quit there. Any questions or anything? Stuff. Yeah, if you guys can think about questions, and it'll slow things down if it's too fast, Hopefully it's not too fast. If it's too fast, ask questions, it'll slow down. Right, just keep asking questions. As many questions you want to ask, doesn't matter. Like, we don't have a fixed amount of stuff we have to cover in here. So if you don't ask questions, I'll just spool through. It can get faster. So.
I was just gonna say our grade was like slightly off from what you marked on our paper versus
Okay.
what we got.
All right,
But I'll send you.
okay, I'll look at it.
I got